This is part 2 of perceiving motion. We had talked about various examples of illusory motion. So we talked about real motion and then compared that to illusory motion, so apparent motion, which really appears much like real motion, and then also induced motion, another kind of illusory motion, and the final one is motion after effects. So when we are watching a stimulus that's moving in a particular direction for a while, we can see this after effect of motion in the opposite direction. So the waterfall illusion is a really good example of, so the motion will be going downwards, as if you have the waterfall, filling up your, not quite all your field of vision, so a good little portion of your field of vision, and you're watching this downward motion. You do that for a good 30-45 seconds. And what's happening there is you are fatiguing those neurons that are responding to motion that goes in that particular direction, and then you will look away and it looks like there's movement going upwards, so in the opposite direction. And the second one I have here is one of these kinds of, it's kind of twisting and it looks like it's going inwards. That in itself is a bit of an illusion, but as you watch that twist inwards, and then when they give you this other screen, it almost looks like, it kind of looks to me like it's waving, but it's supposed to, if it was a different picture, it's supposed to kind of look like it's coming outwards towards you a bit. There's a really great example in the State Museum. So it's one of those where you twist it or you spin the wheel and it looks like there's a little spiral going inwards. And then if you stop and look over at this hanging shark that's hanging from the ceiling that's really large, it almost looks like the shark is coming out towards you. My final example, if you may have had this experience of playing a video game, when I used to watch my nephew's video games for a bit too long, I would stop watching the video game, and so it has this optic flow information so that you're moving forward and that optic flow information is coming out towards you. And this, I would look away or close my eyes and I'd see this kind of movement in the opposite direction. And as we're looking at apparent motion now, Larson and colleagues in 2006 did an fMRI study that found that real and apparent motion activated the same brain region. So research has really started treating real motion and apparent motion similarly. What this is showing, so in A, this would be two boxes coming on the screen simultaneously. In B, this is a box that comes on the screen and then moves in this kind of real motion, even though it is on the screen, so it's somewhat apparent, but it is moving through that space to the second position. And then the third in C, this is basically, it's called something like the phi phenomenon. So a box comes up at the first place in the left, and then with the right timing, the box comes up at the second place on the right, and it has this apparent motion. What we experience is it looks like the box moved from the left to the right. And below each of those is the brain activity. And you can see that when the two boxes come up simultaneously, we have this activity in the primary visual cortex. That's kind of expected there, and it's separated in space, just like the stimuli are separated in space, is that we have that retinotopic organization back there. With real motion, both of those areas are still active and responding because those boxes are in those two areas, but we also see this activity between those two areas as that is where the movement is occurring. And then in C, you can see for the apparent motion, the brain activity looks basically the same as when we have real motion. What are we trying to explain when we're explaining how we perceive motion? This is the trick, and I'm hoping this all makes sense as I'm going through it. So Maria is watching Jeremy, or Jeremy is moving in front of Maria, basically. In A, in the first example, Maria is just looking straight forward, and Jeremy's moving through the scene. And so Jeremy is moving on Maria's retina, and she perceives movement. In the second example, in B, this time Maria is actually watching as Jeremy goes by. So he is staying at the same place on her retina, she's still perceiving movement. As in C, as Maria is moving her eyes from the left to the right, the scene basically is moving to the left on her retina. So there is this movement on her retina, and in this case, she does not perceive movement. So you can see here that we can't really explain how we perceive motion by simply looking at what's happening on the retina. Because in two examples, there's motion on the retina, in A and in C. And only in one of those, in A, do we actually perceive motion. And in B, Jeremy is not moving on her retina, and we still perceive motion. So I have that here in words because I think it's good to explain it from the pictures, but also to have words on here so that you guys can kind of think it through. But you might just want to pause and read it, since this is basically what I just said, that motion detection cannot be explained by what is happening at the retina, and then I go through those examples. Taking action leads nicely into perceiving motion, and part of this is because as we're taking action and we're thinking about J.J. Gibson's idea that our movement guides further movement. So our perception of our own movement is guiding further movement. And remember that what I said about the ecological approach and how he was talking about all of this, it was a very bottom-up theory. And we're going to look at that in the case of perceiving motion as well. He is quoted as saying, "Ask not what's inside your head, but what your head is inside of." So basically the environment that your head is inside of. Again, very bottom-up theorist, even though I think, especially as we've moved forward through time, it seems like we talk more and more about top-down processing, and we do see in the brain these white matter tracts from places like the prefrontal cortex to the visual cortex to where we are perceiving our letters as we read and so forth. And so we're definitely seeing communication back from higher levels of processing down to the lower levels of processing. But obviously, we're always perceiving in a bottom-up direction as well, as if there's nothing out there in the environment to influence our senses, then we're not going to experience anything unless we are having hallucinations or we are dreaming. And even dreaming is a little bit bottom-up. So the way J.J. Gibson talks about this is all in what's happening out in the environment. And what's happening then with Jeremy when he is moving in the environment is that he is causing a local disturbance in the optic array. So remember, the optic array includes things like optic flow, the gradient of flow, the focus of expansion, those invariant pieces of information that tell us about our own movement through the environment or movement in the environment. And in this case, the optic array is this kind of this room, and as Jeremy's moving through this room, he's creating this local disturbance. At one point, we see the window completely. At the next point, he's occluding the window, and then at the next point, he's on the other side of the window. So we're having this motion occur through time. And that is true regardless of whether he's moving across Maria's retina and she's just staying, her eyes are staying where they are, staying still, or whether her eyes are moving and watching, doing this kind of pursuit movement of Jeremy. Then when moving the eyes to the right, the entire scene shifts to the left, but in this case, there is no local disturbance in the optic array. Again, suggesting now that there is no movement. So he does not refer to what's happening at the retina in any real way because he's talking about what's out in the environment. He also has this, as the body moves, we have this kind of global optic flow, which we've talked about in the taking action chapter. But as I'm moving through a scene, the scene is moving around me, but I'm not perceiving it as moving. If it's just this still scene, I'm perceiving that as my movement through the scene. But we really want to understand what's happening in the brain, and we want to be able to account for eye movements in a way that makes sense. So the theory that has done this the best is corollary discharge theory, where movement is detected if this comparator receives a signal that the eye is moving. So we get a corollary discharge signal. So let me just go through the comparator and why it's in quotes there. The comparator is really referring to a brain region that is receiving the signal that the eye is moving. So I'm moving my eyes. My brain is sending a signal to my eyes to move to those muscles, but it's also sending this corollary discharge signal, which is going to this comparator. And the comparator really does deserve to be in quotes because while I'm going to talk about a particular region of the brain being damaged, so it's the medial superior temporal area, really, when we look at the activity of the brain, there isn't some single area that is responding. So they've never, I'm going to say they never truly found the comparator. It is various brain regions, kind of like when we talked about V4, that at some point they thought this was the color region or module, but really it's not a single module. It has this kind of distributed processing. So if the comparator is receiving this corollary discharge signal so that my eyes are moving, or if the comparator receives a signal that an image is being displaced across the retina, so an image displacement signal, from now on I'm probably going to call it an IDS, then we perceive movement. Movement is detected. However, if both a corollary discharge signal and an image displacement signal reach the comparator simultaneously, like as when we were scanning a scene, so I'm moving my eyes, the corollary discharge signal, but also that means image displacement, so there's an image displacement signal, then we perceive that as a stationary target, no motion is detected. And I am going to walk through this with some pictures, even though this really spells everything out kind of clearly, but I feel like pictures help to make it make sense. So for corollary discharge theory, if what I'm receiving is an image displacement signal only, I'm going to perceive movement. So in this case, the eye is stationary. There's a moving person. You can think of this as a bird flying across your field of view or a ball or whatever. Your eyes are still and something's moving across the retina. In that case, we have this image displacement signal, the IDS. The comparator gets that signal and then it communicates to the brain there's an image moving. There's movement out there. If now, so I'm watching the person or the bird or whatever, I'm doing this kind of pursuit movement, what's happening there, right, is that I'm keeping my foveal vision, in this case, on the moving person, and the moving person is staying at the same place on my retina, on my foveal vision. But I'm moving my eyes, and so we get this motor signal sent to the eyes, but also we have this corollary discharge signal that comes off of that and then communicates to the comparator in the brain. The comparator communicates to the brain, the eye is moving, and there's movement out there. It's following some movement out in the world. So motion is detected. Finally, if we are looking at a stationary scene and we move our eyes, let's say over again from left to right, what we're going to see is the image displacement. That image is moving on the retina. Also, we are moving our eyes, and so we're sending that motor signal to the eyes, and coming off of that is this corollary discharge signal. And so the comparator is receiving both of those signals simultaneously, and in this case, it is not sending any signal to the brain. That movement is detected, so we're not detecting motion. Okay, so we have some behavioral evidence of corollary discharge theory. I'm going to start with these behavioral demonstrations. I'm going to strongly suggest that you do the demos that are in the textbook, as they're very helpful. And then I have one here as well. And I'm kind of counting this down. Okay, so you're going to look at the red circle for about 30 seconds. I'm actually going to leave it up here for 30 seconds. And so while I'm talking, and I'm actually going to leave some silence because I don't know what to say for 30 seconds, just kind of keep your eyes as much as possible on the red circle. There's going to be some slight movement, but just keep bringing your eyes back to the red circle for the 30 seconds. I'm hoping I did that for long enough. And if I ask now, what happens when you move your eyes? So I'm hoping that I did that for long enough, and if not, you might want to go back and pause it and actually make sure it's 30, 45 seconds that you're looking at the red ball. What you'll notice is, and I have to answer my own green questions because I'm the only one here, what you'll notice is there is the after image that, like we saw in color perception, has the complementary color. So that ball was red, and now it's kind of greenish. And when you move your eyes, that circle moves with your eyes, right? So what that suggests, that circle is moving with your eyes, it is staying on the same place on the retina because those are the neurons that are fatigued. So there's no image displacement on the retina, but as you're moving your eyes, there is a corollary discharge signal, and so the comparator is receiving just the one signal, the corollary discharge signal, and you perceive movement. Another thing that has been taken as behavioral evidence of corollary discharge signal is, so if you poke your eye, don't poke your eye. Well, very carefully, very lightly. Poke your eye, so I'm just kind of on the outside of your eyelid there. If you poke your eye just a little bit, what happens? So I'm poking my eye just a little bit, and it kind of looks like there's movement out in the world, right? So I'm looking at an X, and it kind of looks like the X is jumping up and down, or a little bit from side to side, up like kind of diagonally. What's happening there is, as I'm poking my eye, there's a muscle in my eye there are the muscles that are controlling my eye movements that are compensating for me poking and moving my eye a little bit. And because we're having this motor signal being sent to our eyes, and again, there's no image displacement, I'm just getting the corollary discharge signal, and so we're perceiving movement out in the world. If we ask about physiological evidence for corollary discharge theory, well, we can see this in somebody who has damage to a particular area. And again, you might think of this area as the comparator, but that isn't the way it looks when we're looking at just at brain activity. But so if we ask what would happen if there was no corollary discharge signal, but we do have image displacement, even though we are actually moving our eyes. So the motor signal is being sent to our eyes, but that corollary discharge signal is not getting received by the comparator. So RW is one of these patients who had some brain damage. He had lesions to his medial superior temporal area. Hope I said that whole thing the last time I said this. So that kind of top part of the temporal lobes, but towards the center. So when he moves his eyes, the images are moving across the retina, just like when we all move our eyes, but because of this damage that eliminated his corollary discharge signal, or the receiving of that in the brain, and so he is now perceiving motion out in the world when there is no motion out in the world. So what little I've read about him, so every time he's moving his eyes, it looks like things are moving. What I've read about him, taking a car ride is very difficult for him because of the amount that we are moving our eyes, and it looks like things are moving so much that he kind of just has to close his eyes sometimes. And I end with this question that sometimes I get responses to, and sometimes I don't. So I want you to think about why we really have to use both something like corollary discharge theory, and we also have to consider aspects of the optic array, or what's occurring in the environment, a la J.J. Gibson. Again, I've had different students really thinking through this question. I have my own questions about corollary discharge theory, and so that local disturbance in the optic array seems very important to me. But I'm going to kind of leave that for you to think about. You might pause before going to the next video and just let yourself think through why we really need to consider more than just one or the other.